In this video, we are going to demonstrate a way to understand how do you find the area of a circle, not inherently already knowing the equation. We're actually going to demonstrate how you could find the equation. This is not a rigorous proof by any means, but it is a visually appealing one. So let us take a look at the circle of A with some particular radius from A to the edge. Okay. This radius has a particular length, whatever it is. Okay. But you could draw like a whole grouping of circles that are ever closer. So any circle can be drawn that has a radius less than this. Okay. Remember, the equation for a circle is pi r squared. So one would have to know that pi exists in order to do this. But what we're actually going to use is the equation of the perimeter, okay, where the perimeter is 2 pi r. Okay? So imagine, if you will, you have your circle, okay, and then you take it as a string and you unwrap that string. Okay? That string will have a certain length. Okay. Since we know the circumference of a circle is the length of that string, we know that this distance is 2 pi r. Okay. Imagine all of these radii, okay, all of these possible radii create different circles, and you unwrap the strings. Okay. Each string will be slightly shorter than the previous one. For how many strings? A total string length of r going up, okay, which I should draw with a straight line. Okay. So this is when the distance is all the way out. Here is when you have the midway point of the radius, if you had a circle that went through here. Okay. And then this point up here is when there's no radius at all. Okay. When it's just the center point, and the circumference of a circle that has no radius is just 0. We're actually going to show you one more just in case. You have a circle at, say, the midway point. Since you have half the radius, though, you're going to have exactly half of the circumference. Okay? So if you were to take a string and unwrap that, that would be some distance away off here. Okay? But each of those distances is a linear relationship. Your perimeter is equal to some number times this, which is basically like the equation that you should be familiar with, y equals mx plus b, where in this case b is 0. It's just a slope, so it's a straight line to connect from 0 to the end point. So what do you have? You have just a right triangle. If you were to stack up all of these strings, they would make up a right triangle, okay, where the height of the triangle is r. Okay. But what is the area of a triangle? Well, we already know the area of a triangle. Okay. So the area of the triangle A is equal to 1/2 the base times the height. In a perpendicular triangle like this one, it's real easy. It's just this times this. So we have 1/2 2 pi r times r, which is pi r squared. The area of the triangle then is going to be the same as the area of this circle. In this video, we're actually going to demonstrate how to do the perpendicular bisector for each type of triangle that we see here, both an equilateral, an isosceles triangle, an obtuse triangle, and a right triangle. Notice that this one also counts for the acute triangle, so we're not going to reduplicate him here. Okay. The perpendicular bisector, of course, just runs through the middle of one edge and perpendicularly. And it's just the perpendicular bisection construction. that we've done before. So in each case, we'll just take our perpendicular bisection construction and demonstrate that for all of them. It looks just a little bit different. Okay. So in the case of the equilateral triangle, you'll see that the perpendicular bisector actually runs through the other vertex. Okay. For this guy, okay, the obtuse triangle, clearly it's not going to be running through the other vertex. Okay. So we again take our points and sweep them out. And we construct our perpendicular bisection line, which just goes there. This is our perpendicular bisector just in the actual triangle. Okay. For this guy, okay, it should be fairly obvious that the perpendicular bisector that runs through the opposite side to the single angle of an isosceles triangle will also run through the vertex, just like it did for the equilateral triangle. But we will again demonstrate that that's the case. Okay. So again, we just have our perpendicular bisector go straight through. It again intersects the end vertex. And then we look at this guy and we say, okay, well, we want a perpendicular bisector, but it's also one that happens to be parallel to this guy. This one is special, the right triangle. Okay? Not the way in which you do it, but kind of what happens and what's important. Okay? The perpendicular bisector, okay, for this guy, when we're not talking about the hypotenuse side, okay, has a special property. It actually cuts the triangle in a lot of ways, bisects it. One, these two are going to be congruent by definition, by definition of the perpendicular bisector. But strangely enough, the other two are as well. So this and this are going to be congruent, as are this guy. Well, and I suppose the other half of him. Okay? So this length is really going to be double what this guy is. Okay? So those are the properties of bisectors. You could draw, again, just like the altitudes and the medians, all three, and they do meet at a similar location, just as the medians and the altitudes for the orthocenters and incenters, etc.